Hi everyone, my name is Aastha Sheth and I study at the University of Texas at Dallas. I'm excited to present my summer research project combining behavioral biometrics, contextual data, and AI for secure adaptive user authentication. In the next few minutes, I'll walk you through the motivation behind this project, what I built over the summer, and what lies ahead. Here's a quick overview of today's presentation. I'll start with the background and the questions guiding my research. Then I'll explain the current limitations in user authentication, describe the solution that I've been working on, and finally share some key takeaways from my prototype that will include the system architecture and workflow, prototype implementation, results and observations, future work and ethical considerations, and where this project could go next. Let's start with the problem. Most of us use passwords and sometimes two factor authentications, but with rising threats like phishing and credential stuffing, these methods are no longer sufficient. At the same time, people want convenience. They don't want to go through multiple steps every time they log in. This project explores how we can make the authentication more intelligent, adaptive, and less intrusive by using behavior and context. Now, before diving into the system itself, I want to set the stage with a bit of background. Behavioral biometrics refers to the unique way someone interacts with the computer, like how long they hold keys, the rhythm of their typing, and how they move a mouse. Contextual data looks at external patterns, such as the time of login, device type, or browser information. All of this data is collected on the front end and structured into feature vectors. These are then passed to machine learning models. In my prototype, I used an SGD classifier. It's a lightweight model that's good for fast incremental learning. However, for larger real world deployments, models like RNNs, especially LSTMs, can be introduced to capture temporal behavior trends more deeply and continuously. These are the four questions that I'll be answering throughout. How can behavioral and contextual data be integrated securely into authentication? Can these signals reliably differentiate users from imposters? How does this affect the balance between security and usability? Can the system defend against attacks like phishing or credential reuse? So let's start with why I chose to explore this topic. This research matters because breaches are becoming more common, and traditional solutions can be either too weak or too annoying. Multi factor authentication is helpful, but having to pull out your phone every single time can become frustrating. My goal was to explore a solution that's both secure and seamless, something that works in the background. So let's start by looking at the current techniques. Passwords remain the default across most systems because they're easy to implement. However, they're also extremely vulnerable. Passwords can be phished, leaked in data breaches, or guessed through brute force attacks. The security of the entire system hinges on secret string that users often reuse or simplify for convenience. To strengthen this, multi factor authentication or MFA adds an extra layer, typically a one time code sent via SMS, email, or an authenticator app. This significantly reduces the risk of unauthorized access, especially from remote attackers. However, multi factor authentication introduces friction. It interrupts the user flow, requires access to another device, and often leads to frustration, especially when the code expires or a user is in a low signal area. Next comes the biometrics. Like fingerprint and facial recognitions, they offer a more seamless experience and are harder to forge, but they come with their own set of challenges. If a biometric template is ever compromised, it can be changed, just like a password. Additionally, these systems rely heavily on hardware compatibility and may not work consistently across all devices or environments, like in poor lighting or with gloves on. Ultimately, all of these methods are static in nature. They verify a credential or characteristic once at login and then they grant access. But what if the user walks away and somebody else takes over? These systems aren't built to continuously monitor or adapt based on usage behavior, which leaves critical gaps that attackers can exploit. So, the core issue with the existing authentication methods is that they're static. They operate in binary way. You either pass or fail. Once that check is complete, the system assumes everything is fine. But in reality, user behavior isn't binary, and threats aren't always immediate. Let's say someone logs in with the correct credentials. That's fine. But what happens 10 minutes later if somebody else takes over the device? Traditional systems don't check again. There's no ongoing verification. They also don't ask, is this user acting like they usually do? They just assume like the person at the login is still the same one throughout the session. Moreover, these systems operate without context awareness. They don't consider when the login happened, which device was used, or whether the behavior matches what we have seen before. And that's a problem because modern attacks are often subtle and hard to detect using one time checks. So, without adaptability, without context, and without continuous assessment, these methods leave major security gaps, gaps that behavioral based systems are designed to fill. So, what's different in my approach? I propose adding a behavioral layer to login by analyzing how someone types, uses their mouse, and the context of the login. The system assigns a confidence score to each attempt. Based on that score, the system can make a smart decision, either approve the login, flag it for the review, or escalate to MFA. This answers part of research question 1 and 2 by showing how behavior and context are being securely integrated and used for classification. And here's how all fits together. The front end captures behavior and context. Passwords are hashed using SHA 512 and verified. Meanwhile, behavioral data is sent to the backend, where it's fed through a scaler and into the trained SGD classifier. The output is a predicted user label and confidence score. This score determines whether the login is accepted or flagged, and the data is routed to their retraining sets. This reinforces research question 1 about secure integration. Now let's get more into the details. Starting with the feature extraction. This is the step where raw interaction data is transformed into a structured numerical format that a machine learning model can understand. In my prototype, I built a Python based pipeline that triggers during each login attempt. As soon as the user begins typing, the frontend built in next.js starts capturing behavior in real time. This includes keystroke hold durations for the 24 keys, average mouse movements, screen width and height, browser type, platform, and the timestamp of the login attempt. Once captured, this raw data is sent to the Firebase Firestores, which serves as our lightweight backend for small scale data storage. From there, the backend built in Fast API pulls the session data, transforms it into a structured feature vector, and normalizes each value using a min max scaler so that everything falls between 0 and 1. This ensures that no single feature can unevenly influence the model just because it has a larger numeric range. This structured feature vector forms what we call a behavioral fingerprint for that specific session. It encapsulates both how the user interacts and when and where they do it, merging behavioral biometrics and contextual data. This setup works well for the current small scale prototype, but it wouldn't be sustainable at a larger scale. For enterprise level systems, we'd replace Firebase with a more robust infrastructure like AWS for storage, Amazon S3 for feature logs, and Kinesis for streaming real time interaction data. We'd also consider extracting more advanced features like digraph and trigraph timings or continuous mouse trajectories to improve accuracy. This modular pipeline is designed with flexibility in mind, so it can evolve as the system grows. The core of the prototype's intelligence is built around an SGD classifier or stochastic gradient descent classifier. This model is efficient, lightweight, and crucially supports incremental training. That means it doesn't need to be retrained from scratch every time a new data comes in. It can just update itself using new samples. The behavioral authentication model is trained using a structured dataset of feature vectors extracted from the user's login behavior. This dataset includes metrics such as keyhole durations, inter-key latency, mouse speed, screen resolution, browser type, platform, and login timestamp. Before training, all features are normalized using a min-max scaler to bring them to a consistent scale between 0 and 1, ensuring no single feature dominates due to its range. Usernames are also encoded numerically using a label encoder so the model can learn class labels effectively. For the prototype, we use the SGD classifier because it's both efficient and supports incremental learning. During training, the model assigns weights to each feature based on how strongly that feature contributes to distinguishing between users. For example, if one user consistently holds a particular key longer than others, that key's hold time will receive a higher weight. Less distinctive features, like common screen resolutions, naturally receive lower weights. These weights are automatically adjusted by the classifier through gradient descent as it minimizes prediction errors. When a user logs in, their behavior is captured and processed in real time. The model predicts their identity and generates a confidence score indicating how close this behavior matches the stored profile. Based on that score, the system decides whether to accept the login or flag it. This architecture creates a dynamic behavior aware security layer that not only classifies login based on past behavior, but also evolves continuously. It balances strong security with practical usability, ensuring that the system remains both effective and adaptive as it sees more data. This directly helps answer my second research question. Can we distinguish between a real user and an attacker using the same credentials? The results here suggest that yes, behavioral patterns do provide enough signal to make that distinction when paired with a trained model like this one. And here's how the decision making pipeline works. Once the SGD classifier gives us a confidence score, if the confidence score is 85% or higher, the login is considered valid and the data is stored in dataset 0, which represents the trusted behavior. If the confidence falls below the threshold, the attempt is flagged and may trigger multi factor authentication and is stored in dataset 1 for suspicious or uncertain behavior. These two datasets serve as continuous learning sources. Dataset 0 reinforces the model's understanding of the legitimate behavior, while dataset 1 helps it learn from the anomalies, potential attacks, or legitimate changes in user behavior over time. The model is periodically retrained using new entries from both datasets via incremental learning, which ensures it adapts to users' evolving interaction patterns without forgetting the past knowledge. What happens to the login data after that? We store every attempt, either in dataset 0 if it looks legitimate or dataset 1 if it's suspicious. These two datasets allow the model to keep learning and retraining, gradually improving its performance. These slide also inc- this slide also answers research question 3. How do we balance strong security with user convenience? By using scoring, and progressive steps like optional MFA, the system remains both secure and user friendly. That brings us to the threat model and evaluation. Our system helps defend against real world threats like phishing and insider misuse by looking at the behavior, not just passwords. Even if credentials are stolen, the attacker must mimic behavior too. This approach makes credential stuffing, replay attacks, and phishing less effective. Addressing research question 4. Looking at the observations, the prototype was evaluated on the sample datasets. While this was an early stage test, the test results showed identifiable patterns that differed across users. The scoring mechanism provided a practical way to make login decisions based on a behavioral fit. These findings support the feasibility of this approach, answering the research question 2 and 3. That brings us to the future work and ethics. There's plenty of room to grow. LSTM models could provide better results for sequences over time. We could even monitor user behavior passively during their sessions to catch hijacking attempts. But ethical use is key. Users should know what's being collected, why is it being collected, and always have the option to opt out. The system must be transparent and never be misused for surveillance. And that wraps up my presentation. I'm happy I'm happy to answer any questions you might have. Thank you.